This video illustrates how computer hardware calculates addition of two numbers, subtraction of two numbers, multiplication of two numbers, and division of two numbers, both the quotient and the remainder. So in order to explain each of these four operations or five operations, I use a simple example. The first part of this video would be an illustration of how computer hardware calculates the summation of two numbers, the summation of two integers, I should say. In all the examples that I show you in this video, I'm going to assume that the integers are 32-bit signed integers, and the signed integers are going to be 2's complement. That means we are not using, we are using basically the same exact notation and standard that MIPS uses, Intel uses, and other CPUs and ALUs that are common, basically used to represent signed numbers. The first example is this. Let's calculate the sum of these two integers. The first one is ABCD 1, 2, 3. Of course, this is hexadecimal. I'm going to show you the decimal value as well, but let's first look at it as a hexadecimal number plus 0x8000123. First of all, because these are 32-bit numbers, if you want to represent the 32-bit number in hexadecimal, you need 8 digits because every digit represents 4 bits. 4 times 8 is 32. So the first thing I'm going to do here in order to show you this, the way these two numbers are going to be added together is to convert every one of them to binary. So in order to convert hexadecimal to binary, every digit should be represented by 4 bits. I have done this in this table that you see. The first number is ABCD 1, 2, 3, 4. This first 4 bits of the first operand is representing A. Then I have B. Then I have C, which is 12. Then I have D. Then I have 1. Then 2, then 3, and then 4, right? This is the last one is 4. So this is the first operand. The second operand is 8000123. This is 8. 1 0 0 is 8. 0 0 0 0. I'm sorry, 0. This was a 1, and then 2, and then 3, and then the last hexadecimal digit was 4, so it should be 0 1 0 0. That's how you convert hexadecimal to binary. By now you should be able to understand how to do this. We discussed this before in the previous modules. The next thing is how to add two numbers in binary. So let's say these two numbers are written back to back, and then the question is, how do we add them? In order to add two numbers, the computers use an approach which is very similar to the way we add two decimal numbers by hand, which is basically digit by digit. We start from the ones digit, then the tens digit, then the hundreds digit, then the thousands digit. Exactly the same happens in binary. use that you know the computer hardware uses the same approach in binary. Basically, what computers use is a sequence of 32-bit adders. Each one adds one digit and it has a carry out. Then the next one uses the carry out as a carry in and adds the next digit. And then this continues for a sequence of 32 bits. I have, I'm going to do it, I've already done it, but I'm going to show you how the third row is calculated based on the first two rows. I'm going to begin by adding these two digits, 0 and 0, the answer is 0. The next one, 0 and 0, the answer is 0. 1 and 1, 1 and 1 becomes 2, and in binary 2 means 2 is basically 1, 0. So the sum is 0 and there's a carry out of 1 here. Let me put the carry outs here so you know what I'm talking about. Then I have 1 carry in plus 0 plus 0, the answer is 1. There's no carry outs, so the next one would be 1 and 1 only. 1 plus 1 is 2, 0 plus a carry out 1. The next one would be 1 plus 1 plus 1, which is 3. 3 is 1, 1 in binary. So there's a 1 in the sum, there's a 1 in the carryout. The next one would be 1 plus 0 plus 0, which is 1, and there's no carryout. 0 plus 0, 0, no carryout. 0 plus 0, 0, no carryout. 1 plus 1 is 2, 0, and 1 carryout. Then I have 1 carry in plus 0 plus 0 is 1, no carry out. 0 plus 0, 0, no carry out. 1 plus 1 is 2, 0, and a 1 carry out. 1 carry in plus 0, 0 is 1, no carry out. 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1. And this goes on and on and on and on, all the way until we reach to the last bit. The last bit is basically the sign bit, because the assumption was these are sign numbers. In 2's complement, the last bit represents the sign. So if it's 1, that means it's negative. If it's 0, that means it's positive. So based on what you see, operand 1 is negative, operand 2 is negative. So let's add 1 and 1. What's going to be the answer? 1 plus 1 is 2 again, 0 plus carry out 1. The last carry out will be dropped because there are only 32-bit of space for the sum, so we'll drop the last bit. When you drop the last bit, it's not necessarily a overflow, so don't think about it this way. It only means overflow if you have an unsigned, if you have the sum of two unsigned numbers. But in this case, we have a signed number in 2's complement, so the carry out of the last bits being 1 doesn't mean we have an overflow necessarily. In order to recognize an overflow for the sum of 2 signed number, you need to follow the following rule. If you add 2 negative numbers and the result is positive, or the opposite, if you add 2 positive numbers and the result is negative, that means you have an overflow. In this case, as you see, the operand 1 and 2 are negative, but the sum is positive. Because of this, you can say we have an overflow. And I'll show you what happened, why we have an overflow. I'll show you a different reasoning for that. Let's continue by representing every single number that we have with decimal representation. The first one is operand 1. Operand 1 in hexadecimal in decimal can be calculated in the following way. You have all the 32 bits, and on top of this number, I have placed powers of 2 from 2 to the power of 0 to the 1 to the 2 to the 3 which is 8, 2 to the 4, which is 16, all the way to the 2 to the 31, with a small detail. The detail here is the last power of 2, which is to the power of 31, must be negative. That's how 2's complement numbers are converted to decimal. First, you write down the power of all the powers of 2 for all the bits, and then these powers become weights of every single bit. The weight of this bit is 1, the weight of this bit is 2, the weight of this bit is 4, the weight of this one is 16, 32, 512, let's say 500, weight of this one is 524,288, so on and so forth. The weight of the last bit is negative 2 to the 31, and that's how 2's complement is converted to decimal. After you write down all the weights, then you need to find the sum product, as you see here, this formula, which is sum product of basically the digits or the bits and the powers of 2. In other words, we want to find the sum of multiplying every digit with its corresponding power of 2. So 1 times this plus 0 times this plus 1 times this plus 0 times this, all the way to the last bit, or I should say bit 0 with weight 1, right? When you do all of that, the answer would be this. So this ABCD 1, 2, 3 that I wrote at the beginning was representing a negative number, negative 1,412,623,820. And the second number, which is 8,000,123, can be converted in a similar fashion to decimal. All you need to do, again, the sum product of the operand 2 bits by the same powers of 2. The answer will be negative 2.1 some billion, right? And when you add these two numbers, because the sum of two negative numbers must be negative, the answer will be this. And this is calculated by just adding the two numbers in Excel. But as you see, the number is greater than the minimum possible integer that you can store in a 32-bit signed 2's complement representation. The minimum number that you can represent in 32-bit signed 2's complement is negative 2.15 billion, which is basically negative to the power of 31. And that's way beyond that. That's way smaller than the minimum. So it's not a surprise that we resulted in an overflow. I told you that sum of two negative numbers came out positive. And this is not going to be the answer. The answer is basically the last row. If you try to convert the last row to decimal using the same approach of multiplying every bit by its corresponding power of 2, and the answer that you will get at the end would be this, which is again the sum product of the sum column and the power of 2 column. I'm sorry, sum row and then the power of 2 row, which is going to be this 734 million something, which is relatively small positive number. If you're wondering what happened to this number that gave us this, I should tell you that in order to get from here to here, you can basically add this real answer by 2 to the power of 32 to get to the sum that we receive by the 32-bit adders that are used in computer hardware. So the computer hardware fails to give you the correct answer, but the answer is not any random number. The answer, which is this number, the positive number, is 2 to the power of 32 short from the real answer. So, or higher than the real answer. So if you want to get the real answer, you need to subtract 2 to the 32 from this number, and you get to this number. You wonder if that's the case or not. I can prove it for you. I will say this minus 2 to the 32. And the answer is the same, right? If you're wondering why this is the case, I should say, remember we had a carry out at the end and we dropped it. That was worth 2 to the power of 32. So again, when you add this, when you subtract 2 to the 32 from this, you get to this, right? So in this case, we had an overflow, but I just wanted to show you how computers do the summation. It's kind of similar to the way we do the summation by hand for decimal number. The next example is a subtraction. We're going to subtract this number. Let me go a little bit closer. This number 8000FFFF from ABCDFFFF. So when you want to do this subtraction, how do we handle that? Again, the subtraction in computer hardware is calculated in the following way. First, the second operand becomes gets negated. Basically, we negate the second operand. So whatever the second operand, in this case 8000FFF, we negate that. We just multiply by -1. How do we do this? Well, you need to find its 2's complement. You need to flip all the bits. That would be 1's complement. Added by 1, that would be 2's complement. And after you negate the second operand, then you add the negated of second operand with the first operand. This add would be basically the difference between the original 2 operands. So what's the trick? First of all, let's do this, the very first step that we did for the previous example, which means convert the hexadecimal to binary. A is 1010, and then B, C, D, F, F. If you go forward, you will see all of that, right? I don't want to explain all the details, otherwise it's going to be a very long video. Then you need to do the same thing for the operand 2. Then this operand 2, which is 8000 FFFF, is next going to be negated. How do you negate operand 2? We're going to calculate its 2's complement. First, the 1's complement, flip all the bits. 1 becomes 0, 0 becomes 1. In order to do that, for Excel, I have done 1 minus the bits. So 1 minus 1 is 0, 1 minus 0 is 1. So that's the trick. And I have negated all the bits, get the 1's complement, then I added by 1. That's going to be basically the value of minus operand 2. You see the difference between this column that is highlighted and the previous one, sorry, this row and the previous one is that this row is the previous row plus 1. You see this bit has changed from 0 to 1. And now that I have operand 1 and its negation, I basically add these two and I call this sum. I should have called that difference because this is basically the difference. Although this is the sum of up 1 and negative up 2, but it's basically the difference between up 1 and up 2. And let's do this. Let's basically do the sum of these two. I'm just going to do the very first few bits, and then you do the rest yourself. So 1 plus 1 is 0, and the carryout will be 1. Again, 1 plus 1 is 2. 2 means 1, 0. 1 is the carryout, 0 is the sum. Now, carryout of 1 plus 0 would be 0 with the carryout 1. 1 plus 1 plus 0 is 0 with the carry out 1. And 1 plus 1 plus 0 is 0 with the carry out 1. As you may guess, we have lots of carry outs here. And this goes forward just similar to the previous example. And we add these two rows bit by bit until we get to the answer, which is this. Now, let's verify the correctness of this difference in decimal. Let's see if this is the real answer, if that answer makes sense. And also, another question, is this going to be resulting in an overflow just like what we had for the addition? When I say overflow, I mean overflow or underflow. In this case, in the first part, when we had an addition of two numbers, we resulted in an underflow. But I keep saying overflow, I meant the same thing. Overflow, underflow. Sometimes the underflow is referred to as overflow as well. Okay, so the operand one's decimal value is this, right? I told you how to do it. Just multiply powers of 2 by each bit. If the bit is in the leftmost location, that would be a sign bit. So you need to multiply it by negative 2 to the 31. But for the rest, you need to just multiply them by the positive to the power of the digit index, whatever the index is. For example, this digit index 27 has a power of 2 to the power of 27. And you basically multiply this bit by 2 to the 27. And then you just add them all together, you get to the operand 1. Then operand 2's value would be, based on the same formula, you get to then this number. The first number is now negative 1.4 billion. The second number is negative 2.1 billion. And then the one's complement of up to, if you apply the same formula, becomes positive 2.14 billion, almost the same as its negation. If you want to get the exact negation, you need to add it by 1 to get the 2's complement. Now this is the 2's complement of this, that's why it's negation of it, right? But to calculate that, we use the same sum product rule. And finally, I'm gonna subtract, I'm gonna subtract up 2 from up 1 by adding this by this. So this is basically the addition of these two, and the answer would be 734 million something. So this is not an overflow. Why it's not an overflow? Because you're basically adding up 1, which is, let me make this highlighted, up 1 is negative. Negative up to, which is 2's complement of up to, is positive, and the sum of a positive and negative number never will be an overflow. Remember that. Overflow happens if you add 2 negative number and the result is positive, or if you add 2 positive number and the result is negative. When you add 2 opposite sign numbers, the result never will be an overflow. Just remember that. That's a very simple rule. Okay, so this is the real answer, and we can verify this answer by basically multiplying these bits by their powers, by the powers of 2. So basically, the calculated difference in that binary fashion will be equal to the sum product of the powers of 2, which is this row, and the last row, let me see. Yeah, the last row. And as you see, we get the identical answer. So that means whatever we did was correct. That's how computers calculate the difference. Basically, they negate the second operand, and then they do the normal summation. Next is an example of multiplication. Multiplication of two numbers like 891 and 0x, 6f's followed by 1, 2. Let's see. This seems to be a positive number. If you convert this hexadecimal to binary, this is what you get. You get a lot of zeros. When I say a lot of zeros, I mean because it has 5 zeros, 5 leading zeros in hexadecimal. 5 times 4 is going to be 20 zeros, followed by 891. 8 is basically 10000. 9 is 1001, and then 1 is 0001, right? And then let me go a little bit down. Okay, so that's basically the two numbers, and that's the first number. The second number would be like 6f's followed by 1, 2. Each f is a 15 in decimal, and then in binary would be represented by 4 ones. So because I have 6 f's and each f is 4 ones, 6 times 4 is 24. So you need to start with 24 leading ones. And then after that, after this, then you need to represent the last 2 digits in hexadecimal with binary, which is 1, 2. 0001 is 1, and 0010 is 2. This is basically the 32-bit representation of the two numbers that you want to multiply. When you look at their sign bits, what you realize is the first number is positive, but the second number is negative. How do computers handle the product of a positive number and a negative number, or in general, the sign, this product of the sign number? First, what they do is they find the absolute value of the two numbers, right? From now on, I refer to the first number as multiplicand, the second number as multiplier. So when they want to multiply the multiplicand with multiplier, they first make sure that both numbers are non-negative. If one of them is negative, they are going to find its absolute value. So in this case, absolute value of A is the same as A because it was positive in the first place. But B is negative, so let's negate that. First find its 2's complement and then add it by 1 to get the absolute value of B. This is the absolute value of B. Right? Now you may say, why did you color all of these with these nice colors? I'll tell you why. There's a reason. As we come down, I'll tell you. What I'm going to do here, I'm going to multiply A by B with the same approach that we do by hand. This is basically the approach that you have learned in your very early years in school, which basically says when you want to multiply A by B, you have to start with the rightmost digit of B and multiply the rightmost digit of B by the whole A. And then calculate the result, write it down. Then you need to multiply the second rightmost digit of B by the whole A. When you find the result, shift that one digit to the left and write it below the previous result. Do the same thing for all the digits of B all the way to the leftmost digit. And when you do that, in every step, you shifted one more digit to the left. At the end, you add all the products that you calculated in the previous steps until you reach to the answer of the product. It's a boring process, it's a difficult process. I'm sure you have done it by hand before, and you have resulted in some cases in errors, human errors. The good news is computers use the same algorithm, but they don't make mistakes because they're computers, right? They're basically logical circuits. They never make mistake. When I say never, I mean with a very, very high chance. Very, very low chance they make mistake. All right. So what I'm going to do is I'm going to basically apply the same algorithm that I just mentioned. Imagine you're just having two decimal numbers, you want to multiply them by hand. How do you do this? B is the multiplier or the absolute value of B. B was negative, so we have to negate it first. And A is the multiplicand. So the first thing I'm going to do is go to the rightmost location and multiply the rightmost bit of B by the whole A. And this is the answer. You get full zeros because rightmost bit of B is 0. And I label this as A times B0. B underline 0 means the bit at index 0, which means the rightmost bit. Then I will do the product of, I will multiply the second bit of B by the whole A. And I draw this with a different color, and the result is colored with that same color. So this is the product of the second rightmost bit of B by A. If you have noticed, I have done one more thing. I have shifted the result one bit to the left, and that's part of the algorithm. That's why there's a 0 at the end. See, this 0 at the end basically shows that you have shifted the result one bit to the left. Same situation happens for the third bit. Third bit of B times A will be written here after shifting it 2 bits to the left. Next bit will you multiply by A, and you write the result after shifting it 3 bits to the left. Next bit multiplied by the A, it's full 0, so shifting it doesn't change anything. Next bit, the gray one, will give you this gray cell, this gray row, after shifting the results of 5 bit to the left. Then the blue cell gives you this blue row after shifting 6 bits to the left. Then this nice color, 7 bits to the left shift operation, or this nice color times this A will give you this row, which is basically the multiplicand, which is A, after shifting it 7 bit to the left, right? And finally, we are going to should I continue further? The answer is no, because the rest of the bits are all zeros, right? So you don't need to continue that anymore. So all you need to do is say, okay, that's it. I'm done, because all the other bits of B are going to be 0, so it doesn't matter what you write because they're all 0. It doesn't affect the final result. Finally, you have to add all of these colorful rows together using the same adder operation that you did for the previous examples. So when you add them all, you just add all these bits, because all 0, the answer is 0, right? Then the next one, you only see 1, 1, so there's the answer is 1, no carry out. All of these, the answer is 1, no carry out. All of these, you only have 1, 1, so it's 1, no carry out. All of these, no 1, so the answer is 0. All of these, you see 2 1s, so it would be a 0 with the carry out. The carry out 1 plus these 2 1s gives you 3. 3 would be 1, and the carry out 1. The answer of these, you have only 2 1s here in this column plus 1 overflow. I'm sorry, carry out. The answer is 1 with the carry out of 1. The 1 carry out of plus this one would be 2. 2 is 0 with the carry out 1. Here I have 2 plus 1, 3, 1k at 1. Same story all the way. You can just verify that yourself. I'm gonna post this so you can see it. And then that's gonna be the sum of all the previous rows, which is gonna be the product of A times B, or I should say the product of absolute value of A times absolute value of B. In order to get the final answer, we need to negate this because one of them, because the sign of the multiplicator and the multiplier were different. When the signs are different, the product must be negative. So after you find the sum of absolute values, you need to, the product of absolute values, you need to negate the product to get the real value. So to negate the real product, to negate the product, I need to first flip all the bits and then add by 1. So this is the final answer, which is a negative number, right? Which is what it's supposed to be. And then I can verify all these calculations by first calculating the value of A. Multiplying A times powers of 2, same story as before. B. Multiplier times power of 2 would be B, which is negative 238. Negative B would be the absolute value of B, which is going to be 238. And then you multiply these two, which is going to be 521,934. This is the same as what we got here. And just prove it, I will do this. Look at that. This is the sum product of row C7 and row C21. C7 is the power of 2. 21 is the one that we just calculated by hand, right? And the answer would be this, right? Which is in accordance of the answer that we were supposed to get, right? Now, when you negate that in the next two lines, you will get basically the sum product of the powers of 2, this row, and the last row. This one I negated it by 2's complement. And the answer is, I think we did something wrong. Oh, okay. Yeah, sorry. Let me do it again. Some product of it's going to be this, comma, this, which is the negation of the previous one. This is the correct answer. When you multiply this by this, you get to the negative 521,930. And then finally, my final example, how to calculate the division. I don't want to get into too much details of division. Division would be kind of similar to multiplication, but you need to do consecutive subtraction instead of consecutive additions. But we're going to ignore some of its details. I just want to show you a very important rule. The first number is dividend. The first operand is dividend. The second one is divisor. The answer of the first line is called quotient, and the second one with the mod operator gives you the remainder. And when you get that, this should be always true. Dividend should be always equal to divisor times quotient plus remainder, no matter what the sign of divisor is, what the sign of dividend is. This equation should always be true. That's the Euclid's first rule of division. This never changes. This is like a universal rule of division, right? That always must be true no matter what. And computers follow this, like all the ALUs that are generated for different CPUs, they all satisfy this rule. The example that I provided is a positive number divided by a negative number. So the first thing we gotta do is to find the numerical value of the two numbers after finding their absolute value. Yeah, A is positive. A basically is a dividend. 891, 0x891 is positive, but I just wrote the absolute value to just emphasize that you need to first find this absolute value. That's how computers calculate the division. In this case, it's 2193. Then you find the absolute value of B. Absolute value of B would be the absolute value of this number. The number negative, if you find this absolute value, you get 238. In order to do that, I have done some ones complement and then twos complement on this. Similar stories. I don't want to go over all the binary versions. You already know based on the previous examples. So you get the values of A and B, their absolute value. Then you do the division in decimal. Let's say the division in decimal is 9, right? This is an integer division. So if there's a fraction, you need to get rid of it. That's why I use floor. Floor means get rid of the fraction, whatever it is. Truncate the fraction. It's not rounding to the closest number. It's just dropping the fractional part. And then I've done a mod operation. Mod is basically the mod on the two positive number that would be a remainder. And the answer is 51. You can do this with any calculator that you have. You don't need to use Excel. But now that we get the absolute value division and mod or quotient and mod, what are the real values for the actual A and B? Because A is positive, B is negative, right? Here is the rule. When you want to find the quotient, if both dividend and divisor have the same sign, it's got to be positive. If they have different signs, it's got to be negative. This rule should remind you of the rule of product of signed numbers. If the two numbers are the same sign, the product is positive. Opposite sign, the product is negative. Same for quotient. Quotient follows the same rule as the product. This is easy, right? So A and B are, one is positive, the other one is negative, so the quotient should become negative. So it's not 9, it's negative 9, right? And this is the most interesting part. The remainder always follows the sign of dividend, no matter what the sign of divisor is. Remainder sign doesn't look at the sign of the divisor. That's not going to happen. Always remainder looks at the dividend, whatever the sign is, the remainder gets the same sign. If the dividend is positive, remainder is positive. The dividend is negative, remainder is negative. If the divisor has different signs, the sign of the remainder doesn't change, right? So in this case, because dividend is, say, is a positive number to start with 0, right? The sign is 0. The value of A mod B would be 51. You can verify all I said by running a program, let's say C program on an Intel or an AMD, or run Java program on any of these and calculate, let's say, for example, 2193 divided by negative 238. You get the negative 9, or do 2193 mod negative 238. You get 51. This is, you can test that, you can do it yourself as well. So this was what I wanted to say about division. Thank you.